Hi, Michelle Glass here, and welcome to our final presentation for our Chapter 19, Lecture 19 series. And our topic for this video is hemostasis, which sounds very similar to homeostasis. So just make sure you are paying attention and reading carefully. Heme, of course, is referring to blood, and stasis is halt or stop or still. So in the case of hemostasis, we're basically just using a fancy term to talk about stopping blood loss or stop bleeding. This is, of course, going to involve that group of cells or cell fragments that we talked about, platelets. There are actually 3 phases to hemostasis, so we'll look at each of these in turn. You have first your vascular phase, immediately followed by platelet phase, which is then immediately followed by the coagulation phase. So they do start like boom, boom, boom. You will see that the boundary between each is kind of a gray area, and there's a lot of interaction happening between each of these phases. So it's not like the vascular phase starts and stops, and then platelet phase starts and stops, and then coagulation phase starts and stops. It's more like around. If you've done that in kind of like a singing group where you have, one group that starts the song and then your second group picks up and starts the song while the first group is still singing, and then you have the third group picking up after the second group has started and everybody is singing together, and then the first group stops first, second group stops second, and third group stops last. So you can maybe think about it in those terms where there's a lot of activities happening at the same time and a lot of interactions occurring between each of these. So let us begin with the vascular phase. This lasts for about 30 minutes and is the immediate response that's happening. This is, of course, coordinated by the cells of the blood vessel. So when a break happens, we start to see contraction occurring of the smooth muscle, and this is going to help reduce the diameter, so less blood is getting lost in this case. Depending on the size of the vessel, this kind of contraction might be enough to prevent, any blood loss. If we're talking about something teeny tiny, like those 4 micrometer diameter capillaries, but when you're looking at like a large vessel, large artery or vein, clearly this is just going to slow down that blood loss. Now, the cells that line the blood vessels are called endothelial cells. These are actually just simple squamous epithelial cells. So they're just lining the vessels here. And we'll be just referring to these as the endothelial cells. So we will see in the vascular phase that they will actually also contract and expose the layer called the basement membrane. They will also release some important chemicals. They'll release ADP. So remember, this is our abbreviation for adenosine diphosphate. They'll release tissue factor, prostacyclin, and also what are called endothelians. The endothelians will just kind of coordinate the vascular phase. So that's going to increase your vascular spasm. So just like maintaining that. And then also start triggering cell division within those endothelial cells and the repair mechanisms to start fixing that break. And then another important thing that we'll see happening is these endothelial cells become sticky. So they begin to stick sort of to each other. And also as those platelets are traveling through circulation, the platelets are going to be kind of trapped by the stickiness of the endothelial cells. Again, if we're talking about a capillary vessel, which is super tiny, it's contracting, and then if those endothelial cells on either side are sticking to each other, this is forming a pretty good little barrier to blood loss. From here, we're ready. Oops, I didn't know I could do that. That's pretty cool. Move it over here. All right, from there, we're ready to start talking about the platelet phase. The platelet phase is going to start within about 15 seconds of injury. So we are seeing that the vascular phase is happening first, but remember it's lasting for about 30 minutes. So it's continuing even while our platelet phase is kicking in. The platelet phase then is going to involve the platelets, and it's going to be coordinated by those platelet cells. So here we see that the platelets will begin to attach to the endothelial surfaces. Remember, the endothelial cells have become sticky. And also remember, the basement membrane was exposed. It shouldn't normally be exposed. So the stickiness of the endothelial cells, the presence of the basement membrane, and collagen fibers being exposed, these three things should not be happening in a normal blood vessel. So the fact that you have a sticky endothelial surface, you have an exposed basement membrane, exposed collagen fibers, this indicates injury has occurred. And as those platelets are moving through, they're going to start sticking. So platelet adhesion is talking about the stickiness of those platelets to the vessel. I was just trying to make that video screen a little bit smaller. The next thing that we see happening is that the platelets begin to aggregate. Aggregation is just a fancy word for talking about clumping. So as those platelets have been moving through and they start to stick to the sides of the vessels and to the basement membrane and to those exposed collagen fibers, then they also begin to stick to each other. So they're adhering to the capillary or vessel, I should say, and then they begin to stick together in a clump. And this is what we call our platelet plug. The platelet plug is like a media sort of response to minimize blood loss, but this is not the same thing as the blood clot. We have not made the blood clot yet. So the plug is just another sort of temporary kind of fix as we are in the process of making that blood clot. The other thing that we'll see happening in the platelet phase is our platelets begin releasing some important chemicals. So we're going to see the release of ADP. This is going to be, of course, our abbreviation for adenosine diphosphate. This is going to increase those platelet that are aggregating together. So this is, a positive feedback mechanism. Platelets are aggregating, platelets are releasing ADP, more platelets are aggregating. We're going to see platelets releasing some chemicals, thromboxane, A2, and serotonin to increase that vascular spasm. So that's kind of perpetuating that vascular phase. We'll also see the release of important clotting factors. The one that we'll mention is PF3. PF3 stands for platelet factor 3. So platelet factor 3 plus the release of calcium will show up in our next phase. We'll talk about that again. So pay attention to that. And then we have also what's called platelet-derived growth factor, which will be important for vessel repair. So again, the platelets are showing up. The platelets are releasing chemicals that are going to bring more platelets to the area that will perpetuate that vascular phase, that will assist with repair, and also clotting factors, which will be important in our next phase. Now, when we talk about that platelet plug, obviously we don't want this to spontaneously occur, and we don't want this platelet plug to be any bigger than what we need. So it needs to be controlled or limited. Your platelet plug is going to be limited by chemical prostacyclin. This is an example of a prostaglandin. So remember, that's going to be like a local hormone that's going to be released through paracrine communication. The prostacyclin is released by those endothelial cells, and it will inhibit the platelet aggregation. So we have some chemicals to stimulate the platelets to aggregate together, and then here we have chemicals to make sure that doesn't get too big. Your white blood cells that are going to come to this site of injury will also be releasing some inhibiting chemicals. So we will see that there are measures in place to make sure that it does not get bigger than what we need. We also have plasma enzymes that are going to help break down that ADP, which remember was a signal for platelet aggregation. And the blood clot, once it forms, will isolate that plug from the rest of circulation. So we will see that it will stop forming. It's not something that once it forms goes outside of control. Okay, so going back to our discussion of hemostasis, we are now ready for that third phase. So now we're going to pick up with coagulation phase. So remember, the vascular phase started initially and it goes for 30 minutes. And then within 15 seconds, we start to see our platelet plug. Well, let me not say that. Within 15 seconds, we start to see the platelet phase starting, and as that progresses, that gets us ready for our coagulation phase, which is starting about 30 seconds, give or take, after injury has occurred. The coagulation phase is the phase that will end with the blood clot. So we are going to be making our blood clot at the end of our coagulation phase. Now, it does depend on what we can describe as clotting factors. These are those things that were released by our platelets. Calcium was one that was mentioned. PF3, you can add that to your list here if you'd like. That was the platelet factor 3. And then there's also going to be some proenzymes that are present in circulation that will be kind of turned on or activated as a result of this process. So the proenzymes, these are going to be things that are in the blood plasma. Okay, so let's look at the steps of what's going to happen here. So we're going to see that there's two different pathways. The first we'll talk about is what's called the extrinsic pathway. And in this case, what we see is that the endothelial cells, if they're damaged, they'll release what's called factor 3. Okay, so if you have damaged endothelial cells, they release factor 3. And then our platelets have been releasing calcium. And you have to have factor 3 and calcium in order to complete all the steps to get you to factor X. We are not memorizing any of those other steps or any of those other coenzymes or factors that are involved here. So they are listed for you in your text. You do have a diagram that shows you that, but we are not memorizing those pieces and parts. My understanding is that this is termed extrinsic pathway because if you are working in the laboratory and you're trying to initiate the blood clot formation, in order for this process to occur, you have to add something to that test tube. Okay. Let us look at our second pathway. Our second pathway is called intrinsic pathway because if you're doing this in the laboratory, everything that you need is already there in your test tube. In this case, in the body, you are starting with an exposed collagen fiber. If those collagen fibers are exposed, you're going to activate what are called proenzymes. Proenzymes are enzymes that are not really turned on yet, so they can't do their job. They have to be tweaked just a little bit. So they have to be like activated to become an enzyme. So a proenzyme is maybe like an enzyme in training. You have to flip the switch before it can actually do its particular job. In this case, the exposed collagen fiber activates some proenzymes, and we don't have to memorize them by name. Those proenzymes then, once they're activated, pair with the PF3. Remember, that's platelet factor 3, so that's coming from the platelets, and calcium, also coming with the platelets, to trigger the formation of factor X. Again, we're going to see that there are other enzymes and factors involved in getting you all the way to the factor X, but we're not memorizing that. The key thing here is that your intrinsic pathway is triggered by exposed collagen fibers, and your extrinsic pathway is triggered by those damaged endothelial cells. And then the other key takeaway is that you have to have things from the platelets in order to get to the factor X. So you have to have calcium, or here you have to have both calcium and PF3 in order to get there. So again, you have to have damage that's occurred, and you have to have the ingredient from the platelet in order to get to the factor X. The factor X is not the end of our story. It's kind of the beginning. So that's what we want to look at next. I forgot I had made this diagram together. So sorry I was clicking around so much. So do you see what's happening here and the difference between? Okay, so let's move on. to what happens next. Oops. So let's start with that factor X. This is initiating what's called the common pathway, because you can take either the extrinsic route or the intrinsic route, and then we're going to see the same events happening. Now keep in mind, if you have damaged endothelial cells, you're also going to have exposed collagen fibers. So you should consider in the body that both of those pathways are happening to take us to that factor X. Once you have factor X, what's going to happen is prothrombin will be, you will activate what's called the prothrombin activator. The prothrombin activator is going to convert prothrombin into thrombin. And it looks like I forgot an R right there. So you can write it in. It's a little bit hard. Oops, that's my crazy R, okay? Okay, so the prothrombin activator is going to be responsible to take that proenzyme prothrombin into thrombin. Thrombin then is going to be required to convert fibrinogen into fibrin. Now, fibrinogen is something that we talked about early on. It's a soluble plasma protein. Soluble meaning that it's in circulation, it's suspended in the liquid component of the blood. Once you have converted fibrinogen to fibrin, the fibrin is going to be a strand that's not soluble. It's coming out of the blood. So now we have these long fibers. You can kind of think about this as like the silky spider web part, and it's going to catch in the fibrin all of those platelets from the platelet plug. And this combination of the fibrin and the platelets are what we call our blood clot. So now at the end of our common pathway, we have actually made our blood clot. Now here we go, taking a look. The significance is that fibrinogen is always in circulation. You don't want it to spontaneously convert into fibrin, because then you're going to have this soluble, this insoluble protein in the way of your circulation and trapping platelets, right? So that would be a disaster. So what we see is you have to have that extrinsic and intrinsic pathway taking us to factor X. And then we have all these kind of steps that have to occur. This is real common in the body that we see this step has to happen, and then this step, and then this step, which triggers that step, which triggers the next. These are called enzymatic cascades. And the significance of the enzymatic cascade is that you have lots of different places where you can kind of give a go-ahead to the process or stop the process. So all of these events would have to happen to actually get to that blood clot. So you should not have blood clots that are just randomly forming in the body. In addition to all of these events that have to occur in the cascade, we do have to have some components from our diet. So calcium was, of course, important. We saw that being released by those platelets. That had to be there in order to complete the extrinsic and the intrinsic pathway. So you would never get to your factor X without calcium. We also will see that the liver is going to use vitamin K, vitamin K to make a lot of those clotting factors. So in order to form those clotting factors, the liver needs vitamin K. You get about half of that vitamin K from your diet. So you're getting it from things like green veggies and grains and organ meats. And then your bacteria living in your large intestine are producing the remaining half. So you're getting about half of your vitamin K from your diet and about half from the bacteria living in your gut. Just so like we talked about that platelet plug needing to have a limitation, we need to have a limitation to our blood clot as well. So we'll see, we get all these steps in order to produce that blood clot, but then we're going to have, like, coming right behind it, some steps to actually get rid of that blood clot. So we have what's called fibrinolysis. So here would be the breakdown, that's lysis of fibrin. So in order for this to happen, you have to have two enzymes present to activate the plasminogen. So thrombin, which we're getting as a result of our common pathway, and then tissue plasminogen activator, which we're getting from our damaged cells. These both are required to get to our plasminogen. Once you have plasminogen, you're going to activate plasmin, and then plasmin is going to be the enzyme that will actually digest that fibrin and begin eroding the clot. So you're making it, and then you're like turning around and tearing it down, so that, you know, of course, you're given the body time to repair that tissue and all that before it's fully destroyed. But it is something, obviously, that needs to be removed once you're finished with it, if you want to think about it that way. Okay, and that is it for chapter 19.